So, today I will discuss about experiment of electron spin resonance. Electron spin resonance is a ESR. It is also called EPR, electron paramagnetic resonance. Both are same basically. NMR is also similar experiment, similar type of experiment. NMR is nuclear magnetic resonance. So, it is basically a magnetic resonance. So, in general let us discuss what is magnetic resonance. So, magnetic resonance, suppose a particle having a magnetic moment mu is placed in a uniform magnetic field of intensity H0, then the moment will precess around the magnetic field H0 with an angular Larmor frequency. That frequency omega 0 will be G E by 2m H0. So, G here is called Landé G factor, G equal to 1 for pure orbital momentum and G equal to 2 for a free electron. And for in general that G, generally we tell Gj, that is equal to 1 plus J plus 1 plus S plus 1 minus L plus 1 divided by 2J plus 1. So, if a magnetic field H0 is applied say along the z direction, then magnetic moment with a particular angle theta, it will precess around the magnetic field. So, this precession is called Larmor precession. Now, if along the y direction, if you apply a very weak magnetic field, then what will happen? And this magnetic field is rotated along the y axis, rotated taking the axis as z direction, then this magnetic field is rotating in a xy plane. Okay. So, then what will happen? This also it will rotate this taking this y direction as a axis. So, there will be another precession because this one extra field, AC field, if I give along the y direction and that field is rotating in a xy plane around the z axis. So, what will happen? So, this AC field here, so it will change, AC field will change, and this here whatever rotation was there, so now this magnetic moment also will rotate along the y direction. So, that time this energy, that angle will not be conserved. Okay. If this field is not there, so all the time it is rotating with this angle theta. Now, this theta will change, when it will precess along the taking this y axis as axis. So, it will rotate. So, that means this theta will change. So, this is a basically classical picture. So, here the change of angle here classically whatever change of angle that is equivalent to the change of the splitting of the energy levels, that is equivalent to the change of the splitting of the energy levels. Okay. So, or it is equivalent to the splitting of the energy level. So, at different angle, so splitting of the energy level will be we will get different energies. Energy level will split it, we will get different energy sub levels. So, that sub levels are basically at different theta. So, that is the analogy with the splitting of the energy level. So, here a particle having a magnetic moment mu. So, this particle, it can be electron, it can be nucleus, or it can be some paramagnetic radical. Okay. So, depending on this particle, so different magnetic resonance, you will see that one is electron spin magnetic resonance or electron spin resonance. Simply we tell electron spin resonance, that electron paramagnetic resonance, nuclear magnetic resonance. So, whatever I told this different name, so basically they works on same principle as I discuss here. Okay. So, to understand this further, so we will consider the quantum picture. So, it will be more convenient, more easier to understand. So, let me tell this quantum picture of this magnetic resonance. So, that spin or nuclear, okay. So, that basically this we can find in the atom. So, atom, it has a nucleus and electron. So, now electrons are in different orbit. Similarly, nucleus also have protons and neutrons, they are in different orbits. So, for the time being, let us not discuss about the nucleus. When we will study the NMR, that time I will discuss that part. So, let me concentrate here for electron. So, electrons are moving in orbit. So, we specify the electron with some quantum numbers, n principal quantum number, L orbital quantum number, and then S spin quantum number. Okay. Then from LS one can get total J, that total angular momentum J. So, here I have written capital L and capital S. So, this L, capital L basically is the summation of the individual L, L1, L2, L3. Similarly, capital S is for individual S of electron, spin of electron S1, S2, S3, etc. Okay. And for a electron, so this total angular momentum small j, it will be L plus J. So, this is the vectorial sum. So, vector model for atomic structure is very successful model. So, from there basically this we have considered this quantum number to specify the electrons in an atom. So, now this whatever the angular quantum number or angular momentum I showed here. So, all of them are quantized in space, all of them are quantized in space, that is called space quantization. so that it is related with the theta, this precession with the angle theta. Okay. So, for different theta, so it cannot take continuous theta. So, that is the quantum picture. It can take only some specific theta. So, that specific theta whatever we are telling, so that is basically because of space quantization of this angular momentum, and that space quantization that we express in terms of magnetic quantum number, ml for orbital, ms for spin, and mj for total angular momentum. Okay. So, for electron spin is s, and its for a one electron its spin magnetic moment, its magnetic moment is mu b. So, mu b is basically called the Bohr magneton, and that is equal to mu b equal to E h cross by 2m. Okay. So, Bohr magneton, you know this, why from here, from this expression you can see it is a Bohr magneton, it depends on the universal constant, that E electronic charge, H Planck constant, and this m mass of the electron. So, these are universal constant. Okay. So, mu b Bohr magneton also universal constant. So, that is why we use mu b like electronic charge E. So, 1e, 2e, 3e, 4e. So, we use as a unit. Similarly, mu b also is used as a unit. Okay, 1 mu b, 2 mu b, 3 mu b to express the magnetic moment of an electrons or atoms. So, the origin of this mu b basically, that is whatever the magnetic moment of an electron in first Bohr orbit, in first orbit of hydrogen atom. So, that is called the Bohr orbit. Okay. So, when an electron in a Bohr orbit, in case of hydrogen atom, when electron, only one electron is there, when it is in this first orbit of hydrogen atom. So, what is the magnetic moment of that electron? Orbital magnetic moment of this electron. So, that value is basically E h cross by 2m. One can derive very easily, and that is why it is called Bohr magneton. So, that space quantization, as I told this, it is showed with this picture. Picture is not properly drawn. I think it should be semicircular. Okay. So, this angular momentum at different angle theta, and so the projection on this on a particular direction in space. So, that is basically the magnetic quantum number that gives magnetic quantum number ml, ms, mj depending on L, S, J. So, due to this space quantization, okay, you will get different energy levels. So, that those energy levels may have same energy, then we tell it is degenerate states. Okay. Now, this degeneracy is removed when we apply magnetic field. Okay. So, then these energy levels having the degeneracy, that degeneracy will be removed, means their energy will be different. Okay. So, that means the energy levels are splitted. So, this one energy level will be splitted in a magnetic field, say is 3, it can be 3, it can be 5, it can be 2, depending on the depending on the value of the quantum number. So, so that splitted energy, okay, that is basically Gj mu h. What is Gj? This in general I am talking Gj. If you take for one electron, so this will be Gs, one electron only spin. If you take only spin, if you consider, then it will be Gs. Okay. If you take only orbital motion and magnetic moment for that, so then it will be Gl. Otherwise, in general Gj. So, Gj, that magnetic moment of this particle, this mu, and this it is placed in a magnetic field H. So, Gj mu H. So, this will be the splitting. So, energy level, actually this energy of the energy level, sublevels, energy sublevels is expressed this way, Gj mj mu j h. Okay. For different value of, for a particular j, it will have different mj value. So, how to find out mj value, that you know. So, it basically mj value will be 2j plus 1. Okay. If j is half, so mj will be plus half and minus half. Okay. 2j plus 1, so j is half, so it is 2, it will be split into 2 energy levels. If j is 1, so it will be mj will be plus 1, 0, minus 1. Okay. So, it will be split into 3 energy levels. So, here you can see the splitting magnitude will depend on G. Splitting magnitude will depend on G. Okay. So, now from this picture you can see, if energy levels are splitted with this Gj mu h, now if you give some external energy, say microwave or the radio frequency wave, okay, wave of radio frequency, radiation of radio frequency. So, energy will be h nu. Nu is the frequency of this wave. So, if you apply this energy in the system, then now this energy will be absorbed by the particle, and it will go up to the higher energy levels. So, that means whatever energy you are giving, that is absorbed, and the particle have sufficient energy to go to the upper energy level. So, so this will happen when the h nu, that energy of the external radiation, okay, when it will be equal to the splitting of that energy level separation. Okay. So, then we tell this condition, when we achieve this condition, we tell this there will be lot of absorption. So, resonance occurs. Okay, occurred. So, under this condition, when resonance occurred, if we can visualize this, if we can observe this, then in this condition, basically these two energy will be same. So, h nu will be equal to Gj mu h. So, from this, so if you can set the resonance condition, and that condition, if you can observe this condition experimentally, then this relation will be followed, and from this type of experiment, resonance experiment, one can find out the value of G factor. So that value of G factor, again G can be GL, G can be GA, G can be GJ, G can be GN nuclear moment, for nuclear magnetic moment GN. So it can be the electron spin resonance, magnetic resonance, it can be the paramagnetic resonance for radical, it can be the electron, it can be the nuclear resonance, magnetic resonance. Okay. So today I will discuss, I will basically demonstrate the electron spin resonance experiment, spectroscopy, it is basically spectroscopy. So electron spin resonance spectroscopy. So we will consider only spin for this class. So only spin of a electron. So electron, it has orbital motion as well as it has spinning motion. So mu L magnetic moment and corresponding magnetic moment for spin is mu S, and together it will be mu J. So for free electron, no orbital motion, only spinning motion. So then we can take this magnetic moment mu as a mu S, and mu S, its value in terms of magnetic moment, Bohr magnitude is 1 mu B basically. For one electron, the spin magnetic moment, the value is 1 mu B. So we write just mu B. And in magnetic field, so energy levels are splitted because of this ms value plus up and minus up. So that energy level will be splitted into 2. So for ms equal to plus up and ms equal to minus up. So this energy levels, that splitting, that difference, this will be del E equal to Gs. As I told here, if we consider only free electron, then we will consider Gs, no orbital, so no total magnetic moment, Gs, then mu is mu V, and this applied magnetic field H. So now, as I told this, if you apply radiation from outside, either microwave radiation or the this radio frequency radiation. See, if its frequency is nu, so its energy will be h nu. So when this energy will match with this difference, then these electrons from the lower state, it will go up, and after some time it will again come down. So it is going to the excited state, and from excited state it will come back to the ground state, normal state. Okay. So in case of electron spin resonance, so then from this relation at resonance, if we can set the experiment to achieve this condition, then from that experiment one can calculate Gs value. So Gs value is basically, what is Gs value? Gs value is basically for pure electron, free electron, that is 2. Okay. Now this value will be varied under different environment. So if we consider the electron spin resonance in solid, not a free electron, say not a free electron. So in case of solid, so isolated magnetic particle is now in a macroscopic body. So it has surrounding, it has different environment. So, that spin now it is not alone, it has so it will interact with the other spins of the neighbors, and there may be spin and lattice interaction. So, due to this interaction, the GS value basically affected and it will deviate from 2. Okay. From this type of experiment, people can measure G value and deviation of the G value from the ideal condition, from isolated condition. So, one can study the interaction with the environment. So, that is basically spin lattice. In terms of spin lattice relaxation time, we express this interaction. So, however, in our laboratory we will use sample having single electron, radical without any interaction. So, it is as if it is just like free electron. Okay. So, that type of sample we will use. So, generally we use the DPPH sample in our laboratory, or most of the laboratory it is used. So, it has, so it is basically diphenyl prickle hydrogel. So, DPPH. So, its chemical structure is like this. So, here you can see on nitrogen. So, it has a single electron, it has a unpaired electron, single electron. Okay. So, in this sample, as if this is and this electron is free electron, almost free electron. So, it is so in this sample, DPPH sample, one can treat that whatever electron are there. So, they are free electron. So, G value we expect that it will be around 2. So, we will do experiment on this sample and we will measure the G value. So, this, so if we go for measurement, whatever theoretical discussion I have done, so from there that environment, that type of experimental setup we have to install. So, we need magnetic field. So one can use electromagnet. So, for teaching laboratory, we here basically we will use a Helmholtz coil. Okay. So, 2 coils. So, their separation will be equal to the radius of the coil. Then one can get the uniform magnetic field between these 2 coils. So, for small field one can use the Helmholtz coil, and at the center of this on the center axis, passing through the centers of these 2 coils. So, now at the middle point of this axis we will put the sample DPPH. Okay. So, now our sample is in the magnetic field. So, now here you can see this, there is a induction coil around the sample. So, and this is RF oscillator. So, from this RF oscillator basically we will excite the sample with RF radiation. Okay. So, our sample now getting magnetic field as well as it is getting the radio frequency wave, right. So, radio frequency wave, its energy is h nu, and the magnetic field, if magnetic field H is applied, then the energy splitting will be as I showed that Gs mu b H. Okay. So, we have to vary one of them, to get the resonance, means the h nu has to be equal to the that energy splitting of the energy levels. So, to get that condition, one has to be variable, one of them has to be variable, and then when they will be equal, then that resonance condition will be occurred, and that resonance condition will be observed in a oscilloscope. It will be observed in a oscilloscope. So, here basically in Helmholtz coil we will apply a DC voltage, we will apply a DC current. So, corresponding DC magnetic field we will get. Now, we will sweep this magnetic field with 50 hertz frequency. So, basically DC now AC component will be superimposed on that. So, it is basically DC plus AC magnetic field will get, the sample will get this magnetic field. So, now you can imagine that for DC field, so the splitting is this. Okay. Now, due to AC component, so the splitting now it will vary. So, splitting of the energy levels, it will vary like this. Okay. Now, if I apply this radio frequency radiation on the sample, its energy is fixed for a particular nu. Now, that nu h nu, that energy will match with some energy separation as it is varying. So, magnetic field is varying, means energy levels daily are varying. Okay. So, we are basically varying the splitting of the energy levels, keeping the radiation, radio frequency radiation of constant energy. Okay. So, due to the variation of the magnetic field, when the energy of this h nu will be equal to this splitting of the energy level. So, at that point there will be absorption, and that absorption, basically here the circuit is there. So, there is a detector and this amplifier I have not shown here. So, whenever the energy will be absorbed by the sample, so corresponding signal will get, and that signal is given to the Y plate of the oscilloscope, and the variation of the magnetic field. So, that signal will be given to the X plate of the oscilloscope. Okay. So, in oscilloscope, this resonance condition, this resonance phenomena will observe. So, that is the basically simple ESR circuit diagram, and this diagram we will use in our experiment. So, as I described, so AC magnetic field with respect to a DC. So, AC magnetic field, it is varying with a particular frequency. It is generally in our laboratory we will use 50 megahertz, 50 hertz, simply 50 hertz. Now, due to this variation of the magnetic field, so the splitting of the energy level will vary, splitting of the energy level will vary. Okay. So, the from oscillator, so h nu, that radiation, it has, so if this is the energy level, this is the energy, so if I express by this level and this level, okay. So if this is the magnetic field, so the splitting of the energy levels will vary in similar way. Okay. So this h nu will be equal you see for a one cycle of the magnetic field. So this energy h nu will be equal to the splitting of the energy level at the 4 point, this point, this point, this point and this point. Okay. So at this 4 point, for one cycle, 4 times energy will be absorbed and corresponding signal will go to the CRO Y plate. So there we will see a peak kind of things, like, so 4 peaks we will see. So now phase shifter is there, so changing the phase shift, we can make this 4 peaks into 2 peaks, 4 peaks into 2 peaks. So from these 2 peaks, so in CRO along the y axis we have applied the magnetic field and along the x axis we have applied the radiation. Okay. Radiation, and then corresponding signal is coming to the CRO y axis. Okay. So there whatever these peaks, 4 peaks, using the phase shifters will make them coincide these 2 with the other 2. So ultimately we are getting 2 peaks. So peak we will see here, you can see peak, we will see that that whatever field, other peak we will see at a on x axis away from this first peak. Okay. So initially what we have to do, basically we have to adjust the x gain of the CRO to make the peak with some at a larger distance. So that distance we can express in terms of divisions. Okay. So if say these are number of divisions are p. Okay. So this p is basically total number of so that's we need to calibrate the magnetic field. So this corresponds to the magnetic field. Okay. Now for resonance condition, whatever peak we will get, so that peak separation, it will depend on this energy, you know. So if this energy, see this, it's lower, so you will see this separation are higher. If this h nu is higher, so they will be closer. Okay. So that again peak to peak, that separation, if this number of division, if it is q during the resonance, if it is q, okay, so that total separation p, it was for a initial magnetic field h, and that field is known to us. okay, and for that field, that magnetic field, so total division was P. Now for Q division, what will be the field? So Q by P, if you multiply this factor with the magnetic field, okay, so then you will get field for resonance, that if it is H0, so your H0 will be basically this separation of these two peaks along the x axis, okay. So that value from CRO itself we can find out, okay. So basically, yes, so this circuit diagram I showed you. So basically magnetic field H, that is from Helmholtz coil, it is formula is 32 pi n divided by 10 square root of 125 this into A is the radius of the coil, so into I. So A is in denominator, I is in numerator, and this N is the total number of turns in each coil, I is the current coil, okay. So one can calculate the magnetic field using this formula for a particular current. So for this field, what is the total number of division between two peaks? So that we have to note down. So that field is calibrated with the number of division of the y axis of CRO, okay. If it is P, then for our resonance condition, what will be the field counting just number of division, if it is Q, that one can find out, So here this value is basically is a root mean square value in case of AC field. So but peak to peak field, peak to peak that from CRO, that we will measure that one basically. So relation between the peak to peak field with the RMS root mean square field. So this 2 square root of this RMS value of field H. So you are measuring this from there, you can find out the H. Now that H, for that H basically during resonance, if this peak separation or Q division, so then this P division was for this value peak to peak, because we are measuring peak to peak. So this value for this magnetic field, that was the P division. So part division, what is the field for Q division, then you can find out at resonance condition. So that will be H0. So basically we have to experimentally, we have to find out this P and Q, okay, measuring the just from the peak to peak value of the magnetic field before resonance condition, what is the magnetic field applied, from there P division, and for a particular H nu this radiation, RF radiation, okay. So what is the peak to peak value for this resonance condition, that division, if it is Q, then we will be able to find out the magnetic field at resonance condition, and then from this equation it should be H0, not H. So one can find out the G value, okay. So and mu B value I have written here, H value also, this is a standard value. So this is the basically experiment electron spin resonance experiment will perform in our experiment based on our discussion in next class. Thank you.